All right, so this is one of the equations you need to know, right? Now, back in the late 1800s, early 1900s, the problem is certain predictions that classical mechanics were predicting were not working, okay? One of them was called black body radiation. Black body radiation is just where you have an object that is not producing light itself, but you heat it up and it starts giving off light, okay? And some of the predictions of how it would do that were not working. And so Planck came up with the idea that light, like if you're heating up your stove top, right, and it starts turning red, so it starts kicking off red light, that's because it has to give off the light in discrete quantities, okay? And so he came up with something called Planck's constant. And, and what he said is that when you relate energy to frequency, energy is equal to E equals H times frequency, where H is Planck's constant, and it is given in your book on page 217, although I'd use it from the end of your book, right, from the last page. Planck's constant is 6.626 times 10 to the 34th joule seconds, okay? H is Planck's constant, which is 6.626.
Is that the R or is that the V?
That's the italicized V frequency. 6.626 times 10 to the negative 34th joule seconds. Okay? And if you're thinking in terms of units, remember Planck's constant now is going to be joule seconds. Frequency is in per second, right? Hertz is per second. So that you end up with the answer in joules. This will calculate it in joules. Okay? So what Planck was saying is that you have these discrete packets of light that have the energy of every discrete package of light that we call a photon has the energy related to the frequency times Planck's constant. Yeah?
And Planck's constant only applies to light particles?
Yes. Yeah, Planck's constant, we're going to use it for various things, but right now it only applies, that's where it came up with it. He came up with Planck's constant, and Einstein in 1905 was actually the one that published the paper about black body radiation. And that's what he eventually received the Nobel Prize for, is black body radiation. Planck's constant is now going to be a constant that we're going to use in several instances to talk about discrete bundles of energy. Now, one thing you do need to remember here is when we do a calculation like this, this is the energy for one photon of electromagnetic radiation, okay? It is not for a whole bunch of photons of electromagnetic radiation. We're going to actually have to multiply in order to get up. Because like, for example, the light that's hitting us right now, that's not one photon hitting us, right? It's actually thousands and millions and whatever, right? Large number of photons hitting us. Yes?
Is there a way to measure photons?
Yes. Yeah, there's different, that's what the whole field of spectroscopy is, right? Is measuring how light is absorbed, how light is emitted, things like that. And we're going to go through some of that. Now, I'm just giving you a tiny bit of history with this. If you want to read your book to get a little bit more, it doesn't go into a lot of details, but it does talk a little bit about, like I said, Planck and Einstein and stuff like that. The next thing that was indicating that there was that light was actually a particle as well as a wave is called the photoelectric effect. Okay, this is where if you have a piece of metal, usually works best, you can do it with other things, but with metal is good, and you hit it with light, electrons go bouncing out, okay? that's called the photoelectric effect, that you can actually produce an electrical current by these photons hitting it. And again, Einstein published the paper on the photoelectric effect in 1905. If you're interested in science history, that is an actually interesting story. He published 3 papers that's sometimes referred to as the miracle year, because those papers were so foundational for all of 20th century science. He published those in 1905, and he was not even working as a professor at the time. He was working in a patent office as a clerk when he published these, which is kind of an interesting story. But anyway, so both of these use this same equation, that energy is related to Planck's constant times the frequency. So we're going to do a